estimated. So if you wanted to run two-stage least squares, you'd regress each of the exogenous variables. Y2, you'd regress on the two exogenous variables, x1 and x2, define the y2 hat, and in equation 1, you use y2 hat instead of the y2. In equation 2, estimating that, you'd run y1 as a function of the exogenous variables. You'd define y1 hat, and then you run equation 2 with y1 hat. Very involved, right, this two-stage least squares procedure. However, if you just went back to the normal equations of all of this is the one defining the error for y1. This is the error for y1 uncorrelated with the first regress of y2. The error uncorrelated with the second regression x1. This is the error for equation 2. This says the error for equation 2 uncorrelated with y1. Error for equation 2 uncorrelated with y2, x2. So you notice that the two endogenous variables here of y2 and y1, I've got them in circles. We can't have them there, right? Because we know that they're correlated with the error. So we have to replace them. So what we're going to do is we're going to replace the endogenous variables with exogenous. So we'll just, instead of the y2, we'll put in x2, the exogenous variable. Instead of the y1, we'll put in the x1, an exogenous variable. So none of these equations are the same. So we can easily look at this and say we have identification. They're all different equations, and each of the parameters, alpha 1, alpha 2, alpha 0, beta 0, beta 1, beta 2, can be estimated. So it's doing this is a good way to see if your system is identified. And I don't know whether you remember, but when you first did, in your very first course of econometrics, when you looked at simultaneous equations, they talked about identification. And there were several chapters talking about the rank and order condition. Right? I can't tell you, you all studied this for the exam and you did well enough to get through, but no one really understands it. In fact, the most frequent call I get is people asking me about identification and rank and order condition. Well, this gives you a lot better way to do it. You can see whether this is identified or not, right? As you have a unique equation here for every parameter. So it's a hell of a lot better way to think about identification. So here's an example where you don't have identification. The y1 is a function of y2 and x1. Y2 is a function of y1 and x1. So we have the three normal equations, the one that defines the error term for y1, the error term for y1 times the first regression, y2, the error term for y1 times the second explanatory variable, and similarly for equation 2. I've got the endogenous variables circled here in brackets, so we need to replace them with exogenous variables, with instrumental variables, because we know that the y2 is correlated with this error. We know the y1 is correlated with this error. However, we've got nothing to put in, right? If we put in x1 here, we've already got it in the third equation. So if we put in x1 here, we'll have the identical equation. That is, we would, with the parameters alpha 0, alpha 1, alpha 2 are not, we can't estimate them uniquely. And if we put in y1 here, we put in x1 here instead of y1, well, that's not going to work either, because then you have the identical equations here, at least. So you can see at a glance that you don't have identification. So that's, this normal, looking at the normal equations of all that gives you a really good way of seeing the problem, just doing one stage estimation and seeing whether you have identification or not. Just checking the chat. Everything's good. Go on to the next slide. So